Hello, in this video we study alternating series. Let's consider the following theorem, and then in this theorem you can see the definition of alternating series. Okay, so suppose that you have a sequence an greater than 0, and the series of this form is called alternating series. So you multiply by -1 to the n, or sometimes -1 to n plus 1, or sometimes -1 to n plus 2, or whatever. Does that make sense? Such series are called alternating series because, the general term in this case, if you compile with -1 n plus 1 or -1 to the n a n, right? So, you have negative terms because in this case, a n is bigger than 0. Does that make sense? So that's why alternating series. Okay, so this theorem says, if you have a n greater than 0, and this series -1 to the n a n and -1 to n plus 1 a n converge if the first condition, limit of a n equal to 0. The second condition, a n plus 1 less than or equal to a n. So what does it mean? That means in this case, the function f of x, which is corresponding to a n, right, is decreasing. Is decreasing. Where, let me write here, f of n equal to a n. And the function is decreasing if and only if the derivative is less than or equal to 0. Does that make sense? So the second condition is equivalent to that. Sometimes you need to differentiate, and you see when it is non-negative. And again, you see this condition all the time, right? For all n. I mention again, we don't need that. This happen for big enough m in here, and then when you start from big enough m, that is okay for us. Does that make sense? So I remember when we study, the integral test, we talked about that already. Like, this function f of x is decreasing, not for every x greater than 1. It is okay for us if the function is decreasing on x greater than or equal to m, where m is big enough. So sometimes that is just, less than or equal to 0 for x greater than or equal to m, where m is big enough. Does that make sense? So we have to pay attention on that. And another comment I want to give before we consider example is this condition, the first condition. So you know that if you have a series, right, and the limit of a n is not 0, so that series diverges. And we say that even the limit of a n is 0, there is not a guarantee that the series converges. Does that make sense? So, but for alternating series, that is not, again, a guarantee, not a guarantee, right? But we need that condition, so we need to check that. Does that make sense? And altogether with the second condition, that will guarantee the convergence of our alternating series test, alternating series in here. Okay, so let's consider the following example. You have series -1 to the n, and from 1 to infinity, 1 over n. So if you write this series, you will see the following. -1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4, and so on, plus -1 to the n, 1 over n. you see harmonic series in this series, right? Because harmonic series look like this: 1 over n, and from 1 to infinity, and this is infinity. We know that by the integral test. But now, if if you add -1 to the n in each term, in general term, 1 over n, so it turns out that the alternating series converge. How? How to see that? In this case, an is equal to 1 over n. And for this an, you see, yeah, actually an plus 1 is 1 over n plus 1, that is less than 1 over n, right? So, sequence an is decreasing. It's obvious. You don't have to differentiate, right? But if you want to see, how that works in general, so you have to put f of x equal to 1 over x. And then you differentiate f of x, you get -1 over x squared, which is always less than or equal to 0. So that means, f of x is decreasing. That means the second condition in the theorem is guaranteed. Okay, so how about the limit of an? Since we have an equal to 1 over n, the limit of an is equal to 0, right? So from here, by the alternating series test, series -1 to the n over n converge. Okay, given that the harmonic series diverge. So that is quite interesting, right? Let's consider another example. Sum of n from 1 to infinity. Here you have n over -2 to n minus 1. So you don't see -1 to the n in this series, right? You don't see that in an explicit form, but it is right here when you have -2. So let's rewrite this series n from 1 to infinity, and -2 is -1 times 2 everything to n minus 1. I write this in the first time, so I try to do that carefully, but you may skip this step in the future. So you have n plus 1 in here, n equal to 1 to infinity. In here you have n, and in here you have -1 to n minus 1 times 2 to n minus 1. And you can bring this, to the top and mention that -1 to n minus 1 times -1 to n minus 1 is 1, because square of that, right? So that is 1. You can rewrite the series as n from 1 to infinity, -1 to n minus 1 times n, here 2 to the n minus 1. Does that make sense? So I hope, okay, let me write it in here. So you have 1 over -1 to n minus 1 equal to -1 to n minus 1, according to this. Does that make sense? All right, so we have an alternating series right now. And the an in this case is n over 2 to the n minus 1. Now let's consider the limit of an when n approaches infinity. That is the limit of n over 2 n minus 1 n approaches infinity. You may use L'Hopital rule, but again, you may use comparison between polynomials and exponential function. Does that make sense? So, yeah, the exponential function at infinity is much faster than any polynomial. So the limit of this should be 0. Or you may use L'Hopital rule, okay? Let me write that if we want to use L'Hopital rule. So you consider the limit of n prime over 2n minus 1 prime when n approaches infinity. So you have limit of 1 over 2n minus 1 times ln2 n approaches infinity, and that is 0. So according to the L'Hopital rule, the limit of this guy should be 0. Anyway, the limit of that guy is 0. Okay, we are good. Now let's check that an is decreasing. So I will do in general way. I will show that the function f of x equal to x over 2 to x minus 1 is decreasing. Okay, so you need to differentiate that. Let's differentiate the function. So you use the quotient rule. I have x prime is 1, so I have 2 to the x minus 1 minus x times 2 to x minus 1 times ln of 2 divided by 2 x minus 1 square. This part is the derivative of 2 to x minus 1. Okay, we can take 2 to x minus 1 out because that is common, right? Then I have 1 minus x ln of 2 over 2x minus 1 square. It does not bother us. We don't need to simplify all this term. We just need the sign of the derivative, but both factors are positive. So the sign of the derivative is decided by this term. And you see, for big N of x, I can draw in here. For big N of x, 1 minus x ln of 2 is less than 0. Okay, so that means the derivative is less than 0. Here I think it's enough to pick x equal to 2 or maybe 3. Okay, but that's okay. The most important is the function is decreasing. I will write here for x greater than or equal to m. Yeah, big enough in here. Does that make sense? All right, so this is less than 0. That means, our series satisfy both conditions of the alternating series test. So we write here by the alternating series test, our series converse. Oh, sorry, here we should not have an, right? We still have, negative 1 to the n minus 1 an converse. That's it. That's how we can use alternating series test. But again, right, I very recommend you to do this way. Write the function, the corresponding function for an, and show that the function is decreasing. Any tricks are good, as you have seen in the textbook, that they do some, comparison. But in my opinion, that is not very natural. So the very natural way and the very easy way is to consider the function and its derivative. It is much easier and very straightforward. You have function, differentiate that. You see if the function is decreasing or increasing. Does that make sense? All right, before we finish the video, let's consider some series when the alternating series test does not apply. Okay. So let's consider the series negative 1 to n plus 1. In here you have n plus 1 over n from 1 to infinity. And in this case, n plus 1 over n. Right? So you see, an does not have limit equal to 0. The limit of this guy is 1. So you cannot apply this alternating series test. But that does not mean that the series is diverse, okay? Let's write it at least one time. That does not mean the series diverse. Don't forget that. So we cannot apply the alternating series test, but that does not mean, the series diverse. Suppose that you have some alternating series which is convergent, and you want to approximate the sum of this series. So how to do? Look at this. Suppose that the convergent alternating series satisfies the condition an plus 1 less than an, right? Then the absolute value of the remainder Rn involved in the approximating the sum S by Sn, where Sn is the partial sum, is less than or equal to the first neglected term. That is, S minus Sn absolute less than or equal to absolute of Rn, and less than or equal to An plus 1. Okay, let's write this, right, in an explicit form before we consider some examples. So, let's say you have negative 1 to the n, an in here, and from 1 to infinity. So that is negative a1 plus a2 minus a3 plus a4 and so on, plus negative 1 to the n, an, and so on. So what is Sn? Sn is partial sum. So that is sum n from 1 to the n, right? Negative 1 and an. Does that make sense? So basically, if you write it, you have negative a1 plus a2 minus a3 plus so on, plus negative 1 to the n capital, a n capital. Okay, so that is partial sum. If our series right here satisfy the condition a n plus 1 less than or equal to an. Okay, so you see this condition in the alternating series test. But, we have a lot of alternating series. And we have alternating series tests to test a series if it is convergent or divergent, right? I say if it is convergent, we don't use that to test the divergence. I'm sorry. But not every convergent alternating series satisfy this condition. Does that make sense? So please don't be confused with that. Not every alternating series satisfy this condition. But if your alternating series satisfies this condition, we may use, this inequality. Does that make sense? So let's consider the following example. Let's approximate the sum of the series by its first 6 terms. Okay. So basically, we need to find, the S, right? Does that make sense? We need to find the S using Sn in here, where n is equal to 6. Okay? But of course, the most important is, you have to find the error of your approximation. That means the remainder. Is that correct? So you're seeing here that means the remainder in here is just absolute. You can find the upper bar of the remainder, and that is more important because if you just calculate, like, okay, give you a number n equal to 6, so you can take sum of the first 6 terms, right? It's okay. You have some approximation. But how to evaluate the error, the remainder? That is much important. Does that make sense? So I can find S6. Firstly, we need to find, okay, I don't have series yet. Okay, sorry for that. So my series is -1 to n plus 1, 1 over n factorial, n from 1 to infinity. All right, remind you that n factorial is product of the first n integers, right? And of course, according to the alternating series test, you can see that the an is n factorial has limit equal to 0 and an plus 1 less than or equal to an. All right. So this alternating series test, this alternating series converse, and this condition is satisfied. That's what we need. From here, you can find S6. Okay, S6 is equal to, so you just plug n equal to 1, 2, 3, 4, 5, 6. So you have -1 square 1 over 1 factorial plus -1 cube 1 over 2 factorial plus -1 to the 4 1 over 3 factorial plus -1 to the 3 over 1 4 factorial plus -1 to 6 times 1 over 5 factorial and plus -1 to 7 1 over 6 factorial. Okay, so that those are first 6 terms, right? Let's simplify. So you get 1 minus 1 over 2 plus 1 over 6 minus 1 over 24 plus 1 over 120 minus 1 over 720. Okay, so just apply this formula for factorials, right? And find all factorials in here. 1 factorial, 2 factorial, 5, 4, and 6. And then you simplify this number, you get 91 over 144. And this approximately equal to 0.63194. So that is your S6. So with this number, what is the remainder? The remainder Rn, R6, let's say that, absolute, equal to all S, that is the series, minus S6. And according to this inequality, that is less than or equal to Am plus 1. Okay, less than or equal to A7. Because the next one is 7, is it? So the 7 is 1 over 7 factorial. That is 1 over 5040, which is approximately equal to this number, or you can buy 2 times 10 to negative 4. All right, so you see, that is your remainder. Is it correct? Then what does it mean? That means you might use S6 to approximate S with this arrow, or you can write in the following way. Okay, here's your S6. So plus minus 2, I write here S6 plus 2 times 10 to negative 4, and then S6 minus 2 times 10 to negative 4. So your S should be in this neighborhood. Okay, your S should be in this neighborhood. Does that make sense? Or you can rewrite, okay, that is, S is greater than or equal to S6 minus 2 10 negative 4 less than or equal to S6 plus 2 times 10 to negative 4, or S less than or equal to 0.63194. 214 and then greater than or equal to 3.63174. Does that make sense? So, basically, this is how we can, approximate an alternating series using this inequality. And of course, we need this condition. So, if your alternating series satisfies, the alternating series test, so you are free to use it because, this condition is already in the alternating series test. Does that make sense? All right, so I think I've stopped my video in here. If you have any questions, please feel free to let me know. Bye-bye.